All right, talking about arc length and curvature on three-dimensional space curves, which we covered arc length before. Curvature is a little different measurement than we've talked about before, but you know, in the arc length, what we're basically trying to do is from a point, call it the base point or start point, whatever you want to, we want to measure the length along just the curve, right? 1, so that's 0, then that's our reference point, and then we go 1 and then space them off equally there. So we're trying to find, you know, from here to here, whatever, what's that length? And yeah, we refer to this this point a little more than previously, but that's what we're doing. We're trying to find the length along the curve. As long as it's a smooth curve, we're good, right? If it jumps around, we have a little problem, but we're going to be dealing with the smooth curves, as they call them. Okay, now from previous work, if we had a parametric equation, say x equals f of t, and then the y was equal to some g of t, from that setup, we found out, do you remember what the arc length L was from A to B? It was the integral from A to B. It was the square root of the derivative squared. Yes. So f prime of t squared plus g prime of t squared dt. Yes, okay. Uh-huh. Exactly. All right. Well, when we go to vector functions, space curves, if you will, if you have a smooth curve, so if our vector function f of t I plus g of t j plus h of t k, if that defines a smooth curve from A to B, t equals A to B, then the arc length L equals the integral A to B of the very same thing. The square root of f prime of t squared plus g prime of t squared plus h prime of t squared. Okay? But, as mentioned there, this can be compacted a little bit, because what is the square root of all these derivative squares? What is that in terms of, in other terms we could put in? It's the magnitude of the derivative vector. So if this is our vector function, then the derivative, of course, would be f prime of t I g prime. That's just the magnitude of, yeah, it's the magnitude of the derivative function, which we can denote this way, right? And so that's a much more compact way, or nicer way of remembering it, I guess. Yeah, it's just the magnitude of the derivative vector. Okay. All right, so let's say we've got a glider, and it's soaring from or upward along the helix here, defined by r, vector r equals cosine ti plus sine tj plus t. Okay, that might look familiar there. That's our little circular helix, isn't it? Winding up its way. All right, so what how long is the glider's path from t equals 0 to 0 to t equals 2 pi? Well, that's our arc length, isn't it? Which is the magnitude, a to b, magnitude of the derivative vector, integrated from a to b. All right, so what is our derivative vector going to be? Cosine negative sine t I plus the cosine tj plus 1. Okay, yeah. So then the magnitude, all right, so we're going the integral 0 to 2 pi. That's our a and b. And then the magnitude of that would be the square root of sine squared, so negative sine squared. So that'd just be sine squared. Plus the cosine squared plus 1 squared. And as we know, that's going to, this and this will turn to 1. So we've got the square root, what's dt? Square root of 1, yeah, that's 1 plus another 1, so we get the square root of 2. All right? And so that then integrated would be the square root of 2t, and then 0 to 2 pi, well, that's just going to be 2 pi times the square root of t, 2, right? That would be the number of units that this particular glider would fly. A little bitty one, okay. Huh? Yeah, so it's gone full circle. But notice here that it's gone a little more than just the diameter of a circle, hadn't it? The diameter of this circle would be, this would be a circle of radius 1, if you just look at it on the xy plane. And so that would be 2 pi. And so what's added to it as it circles up with that is by factor square root of 2. Interesting little note there. Okay. All right. Now, something else they mention here as well is the idea of reparameterizing the curve. And we're going to reparameterize, basically go from time, our parameter basically has been t, time, and so we're going to reparameterize with the arc length. And so here's, if I can spell it, hard enough to say. Okay, so let's say we've got this little curve right here. All right, So we've got a point. We're going to start there. That's going to be our start point, base point, whatever you want to call it. All right, and so then our curve just kind of takes off and then maybe loops around a little bit, but whatever. Okay, so this is our starting point. So that's usually we're calling that A, point A. And so this, if we do it in terms of a vector function, then that's our starting point. So that's the vector evaluated at A. Okay, so what we're going to do though is take it, reparameterize this based on the arc length, and so we're going to go out to an arbitrary another time, and so that's going to be just time t out there. And so this right here is this what we'll call S of t from here to here. That's going to be the arc length, of course, but we're going to reterm, if you will, our parameter, and we're going to make it in terms of s instead of t. Now s is of course dependent on t, but you'll see how we can do this. Basically we're going to go from these t's to in terms of s. All right, so here's what S of t is. Of course, S of t is the arc length, and so that's the integral from A. Now, like I said, we're letting t kind of be the variable here, and so we're not going to specifically say a value. We're going to let t vary, and so A is going to, we're going to go from A to t now. And then S is the arc length, so it's the integral of the arc length. And since our t is here, we don't want to use that variable here, so we're going to go to a different one. So that's S of t. Now, if we differentiate both sides, this is also critical here. Differentiate both sides. With respect to t. Here's the way they're going to write it. ds dt, then, that would be the derivative with respect to t, equals, then, from the fundamental theorem of calculus, what we get here, just the magnitude of the derivative vector. Yep. Kind of basically reversing the integral reverses there, so yeah, okay. All right, so this will allow us to reparameterize, and we'll see how here in a moment. Let's just do one to kind of see how it works. All right, so let's reparameterize our helix cosine t I plus sine tj is tk. S of t is just going to be a function, yes. It's not going to be a vector. Yeah. So we're going to reparameterize with respect to the arc length. measured from our initial point 1, 0, 0, which note that that is time times 0, in the direction of increasing t. And, you know, the way it works out then, if we go in the direction of increasing t, then if we want to go backwards, it would just be a negative. Those would be negatives. But we'll go with the increasing t on this one. All right, so here's what we basically want to do. We want to change from our vector being r t, we want to go to the vector in terms of s. In other words, we're using a different parameter. Instead of time t, we're using arc length s. All right, so what do we know about it? S equals the thing we just defined. S is the S of t, which is the integral a to b of the derivative magnitude, sorry, a to t, and also ds dt is just the magnitude of r of t. Okay? All right, now we already know something about this one. I'll do another one from scratch here, but we already know this about our particular function here. We found that just a moment ago. The magnitude r prime of t you know, we went through it. It's that squared, well, the derivative squared plus derivative squared plus derivative of that squared. It was square root of 2, wasn't it? It was square root of 2. So from previous work, we already knew that that was a square root of 2. And so our derivative, the magnitude here, and so s, or s of t, is going to be the integral from a, which in this case we know is, we're starting at t equals 0, so that is 0. 0 to t. And we know this magnitude is the square root of 2. And so s is just going to be that integral, which is, oh, sorry, du. Just using u because we already used t here. You could use whatever we want, but easy integral, that's just the square root of 2u. And we evaluate that from 0 to t, we get the square root of 2t. Right? Now, the goal was, though, to go from r, the vector in terms of t, to the vector in terms of s. Well, we now know that s from this work here is equal to the square root of 2t. And so what could we replace t by? S divided by the square root of 2. From this work, we know that the s would equal the t would equal the s divided by the square root of 2. And so just by a little resubstitution here, we now know t is s over the square root of 2. Which means that is our cosine of s over the square root of 2 I plus sine s over the square root of 2 j, and then s over the square root of 2 k. Okay? I believe that's the way they want it. Yep. All right. All right, here, let me get time here, so let's do another one. Do what? S is the arc length. Which is just measured from this initial point. So yeah, in that case, yeah, it would just, if they you're talking about giving you a value, what values would you plug in there?
Oh wait, so if you plugged in that for x, you find points where you
Yeah. Yeah, and it's based on this initial point. Yeah. So if you want to travel 1 unit or 2 units or 3 units, so yeah, you're just giving the s instead of the time. You're giving how far it goes.
Does units change too much? Like what you have to use just think of it like seconds, minutes, or something. But heads.
Yeah, I mean, yeah, you'd have to.
I guess it depends on what you're doing. Yeah.
Depends on what you're doing. Yeah.
Whatever displacement you need to use.
Okay. So let's reparameterize. R t. This one's the cosine t plus t sine t minus t cosine t. Obviously, these are chosen well for what happens. Okay, you know, that's what we did with the arc length before. We chose nice values or nice functions. Okay, so reparameterize that with respect to the arc length s. And we're going from t equals 0. Okay, so s, or s of t, is integral 0 to t and the magnitude of the derivative vector. So that's what we need first, right? We need the derivative vector. Derivative vector is what? Negative sine t plus, little product rule there, t cosine t, and then sine t times 1. And then the derivative of that would be cosine t minus t times negative sine t, and then plus cosine t times negative 1, so it would be minus cosine t, and then of course, derivative of 0, 0. And that's why we chose this one, because we just get t cosine t, t sine t, 0. So then the derivative, whoops, it's the derivative. Then the magnitude of the derivative would be the square root of t squared cosine squared plus t squared sine squared plus 0. But notice that if we factor off the t squared, what do we got? T squared times 1. So that's just the square root of t squared, so that's just t. That works out pretty good, doesn't it? All right, so back to s here. S then is s of t from 0 to t. Now we know the magnitude is, well, it turns out it's dependent on t. So the magnitude of the direction vector, if we're doing it in terms of u, would just be u, right? So our magnitude is just whatever u, and then we want to integrate that u to u, so that'd be u squared over 2, be the integral there, from 0 to t. That's t squared over 2. That is our s. But, yeah, solve that for t to get our replacement here. So that would be t squared equals 2s, and so t would be the square root of 2s. Well, since we're doing increasing t, yeah, we'd go with the positive. Yeah, because you're right, could do a positive or a negative s, square root there. But since we're going from t equals 0, implying increasing, they'll want the increasing one. That would be the square root positive. All right, so our vector reparameterized now in terms of s would be the square root of 2s, and so that would be what? So instead of t, I'm going to do the square root of 2s. So it would be the cosine of the square root of 2s plus the square root of 2s, sine of square root of 2s. That would be the I component. This j, then it would be sine of square root of 2s minus square root of 2s, cosine square root of 2s, and then 0. All right. Not quite as elegant, I guess, but nonetheless, that's what it is. And again, I meant to mention this on the other one. This is useful or helpful because it's just natural to think about something in terms of its length, not just its time, but how far it travels, the s. And also, this is not dependent on a specific coordinate system because you're starting, wherever it starts and going from there. So anyway, a couple of things they pointed out why you might want to do that. All right.